Oh, you're still here. I didn't scare anybody into dropping the class. That bar and bracket stuff, what you really need is practice, okay? We're going to see some examples of it in this part of the lecture here. Everything I've shown you so far in this lecture was about what models are telling us about the changes in temperature in the near-term climate. Let's kind of start getting more general than that and talk about changes in the water cycle. Because remember, back in the first module of the course, we talked about the fact that in a warmer world, we're expecting some kind of intensification of the global hydrologic cycle. We're expecting more evaporation, we're expecting more water vapor in the atmosphere. We expect, therefore, since evaporation in the long run has to be balanced with precipitation, a world with more evaporation has to have more precipitation, but they don't necessarily happen at the same place because water gets transported by the wind. This is a complicated set of issues as to what's going to be happening with regard to precipitation. And of course, the IPCC 5th Assessment Report has examined this in great detail here. And so we're going to be picking apart a set of diagrams here that show changes in precipitation based on the RCP 4.5 model run. I know you can't read this plot because it's too small. We'll zoom in on the parts we need in just a moment. But just broadly, looking at these diagrams here, you know, we got 4 different seasons and all this kind of stuff going on here with these different model runs. The first thing I want you to notice is that there's areas on those plots that are blue, and there are areas on this plot that are brown. And if you actually look at the key of the diagram there, blue means more rain, and brown means less rain. And they're all kind of small values. I mean, actually, they're all pretty close to that 0 threshold right there, right? I mean, other than that one kind of little blob over Africa right there, the models seem to pretty much be saying there's not huge changes in the amount of precipitation worldwide. Okay? Alright. So if we actually zoom in with my little magnifying glass tool, if you look at the 42 members of this particular model ensemble here, you can see that there is a lot of parts of the world where there is more precipitation, and there are some places, particularly at subtropical latitudes, like about 30 degrees north and 30 degrees south, the places where the world's deserts are. There does seem to be a decrease in precipitation in some of those regions. Of course, those are places that don't really have that much precipitation anyway. I mean, decreasing the amount of precipitation over the Sahara by 10% doesn't exactly change it from being verdant cropland to being a desert. It already is a desert. I mean, we're not changing it all that much. I do want to draw your attention here, though, to the cross-hatching. Remember, the cross-hatching meant bad news from a point of view of science. It means that the 42 members of this ensemble had such a large range between them that we can't necessarily have much confidence in this result. This is the average that they're showing here, but they're saying, you know, some were below, some were positive, some were negative, some were, you know, we don't really have that much confidence. And again, exactly how they define that stippled area is described in the book. That's not what's important, but the basic idea that there's so much variability between the 42 different members of the ensemble that maybe we can't yet make this kind of level of understanding, which is a real drag. Because frankly, this is one of the things that, from a point of view of the public and policymakers and stakeholders and so on, this is one of the things we most want to know. Everybody's worried about desertification, right? If we're doing something to make the world more a desert, or even to make certain regions more a desert, we really want to know that. Alright? For that matter, everybody's also worried about possible changes in the distribution of precipitation with regard to flooding. I agree. We all want to know that, but maybe we're not looking at this right. We certainly should be worried about such things. Those are high-impact climate events, and they certainly will happen. Well, not necessarily everywhere, but at least at some places, there's going to be places that have more precipitation. There are going to be places that have less precipitation. But what the models are telling us is that we do not yet have enough information to reliably predict where and when those kind of changes are going to happen. Which sounds like a bummer. It is kind of a bummer. I mean, we really would be better if we had good answers, but if you don't know, it's better to admit you don't know. But that doesn't mean that there aren't things we can learn about the hydrologic cycle from these models. And look what we've got here, some brackets. Yeah, okay. So I have some bracket terms here. We're making some zonally averaged plots here. And there's 2 plots here that we're going to keep coming back to over and over again. The one on the left is going to be zonally averaged precipitation change. So delta P, as in change in the amount of precipitation that those locations were receiving at the beginning of the model run, to what they were receiving, I don't remember, 2035 or 2050, it doesn't really matter. That's how precipitation is changing, and it's zonally averaged. So like we're seeing how precipitation changed along the equator, how precipitation changed along 30 north, how precipitation changed along 60 north, etc. The one on the right is change in the moisture budget, change in precipitation minus evaporation. Bracket delta P minus E. Oh my gosh, this sounds painful. Maybe we need some information here. Now, to establish some context. Now, to understand what's going on these plots, by the way, see how there's sort of 3 different colors on each one? There's a gray, a dark blue, and a purple. Those are indicating different ranges that the 42 different models fell in, okay? Think of the area as being like the gray area in the middle is where most of the models fell, but like the purpley area shows where the outliers of the models fell. So they're not, you know, that kind of gives you a sense of the uncertainty. It's, again, kind of like a spaghetti plot. Not exactly the same notation as a spaghetti plot, but again, it's giving us a sense of what the ensemble of models were doing. And again, this is for a particular radiative forcing. I think this is the 4.5 RCP, but it doesn't matter from our point of view. Just to give you a little context as to how to understand this plot, I thought I'd show you something else. This is a set of plots that indicate P bar bracket. This would be the precipitation, the average precipitation. I think this is, it's averaged out to be millimeters of precipitation per day. This is probably over a 30-year period or something like that. And it's bracket. So we are zonally averaged. And you can see a bunch of features of the global climate on this diagram here. Now there's actually 5 different curves on that diagram. They're different data sets, okay? But they all, you notice, have very similar characteristics there. And you can see, for example, the intertropical convergence zone, that band of thunderstorms that circles the Earth around the equator. See how there's all that precipitation? If you look on the x-axis as to where the equator is, you can see that we have the highest precipitation rates all around the world are in the ITCC region. You can see the world's great deserts at about 30 degrees north and 30 degrees south, whereas that local minimum there in the precipitation, where they only are averaging about 2 millimeters per day. Now you might think that still sounds like a lot of precipitation for something like the Gobi Desert or the Sahara Desert or something, but keep in mind this is only average all the way around the world. Not every place at 30 degrees north or every place at 30 degrees south is inside of one of the deserts. Notice you can see like how dry it is up near the poles. You can see how low the precipitation gets at like 85 degrees north and 85 degrees south. Just gives you a little context about these changes in precipitation. Similarly, I could show you for context what a map of P minus E looks like. Now, I had a hard time finding a good plot of zonally averaged P minus E. The one I picked out from here, from this website you can go to, the solid curve is the one we want to look at here. Don't worry about all these dashed dots and all that kind of stuff. Just look at the solid curve here. And what I want you to notice is that that is zonally averaged P minus E. How much precipitation fell minus how much evaporation occurred at that location. And there's a interesting little pattern of positive, negative, positive, negative, positive that goes across here. Notice, for example, that across, again, we're just establishing context. This is just the observed climate we already have. Like, notice how from about, I don't know, maybe 10 degrees north to 10 degrees south, we have a positive value of P minus E. There's more precipitation that happens in that part of the world than evaporation. In contrast, from about maybe 40 degrees north to about 10 degrees north and about 40 degrees south to about 10 degrees south. See how P minus E is negative? There's relatively little precipitation, but lots of evaporation, especially over like the subtropical oceans and so on. Just a little context then as to how there's different parts of the world that have more precipitation than evaporation, and how in some parts of the world there's more evaporation than precipitation. We have to transport water from places that are consuming too much water. You know, there's too much water vapor being removed from the atmosphere by precipitation. We have to move it from places where there's too much evaporation happening. Oh, okay. Let's go back then to these climate change things. Remember, this is then how precipitation changes over the next few decades. Well, look at that area I've circled there in red. That is the area where the zonally averaged change in precipitation, so bracket, well, it would be read delta P bracket, is positive. So averaged all the way around the world at like the equator, almost all the models are showing an increase in precipitation. The amount of precipitation is increasing. It's already high, and they show it increasing. Okay, it seems to indicate then that in the tropics there's going to, in general, be more precipitation. All right, especially more rain in the ITCZ. Okay. And then you take a look at like the subtropical latitudes at about 30 north and 30 degrees south, and what you see is that the change in precipitation is, well, it might be a little drier. Certainly in the southern hemisphere one, it looks like it's a little bit, the gray area is mostly below zero, but they're both pretty close to zero. It's maybe a little drier in the subtropics overall, but if you're worried about the subtropical deserts growing and expanding, the models are not seeing that yet. At least with our current understanding of the physics, that doesn't seem to be happening in these models. Okay, I found a mistake in the last little bit of this lecture here, so I'm piecing in another from a different day when I fixed this. Remember, we're looking at these curves here that show how things changed from, before the, well, basically at the present until roughly the middle of the 21st century, and so that's what the deltas here. This is zonally averaged precipitation on the left and precipitation minus evaporation on the right, and there certainly are statistically significant results here on that right panel, where we see, like in the subtropics, that the change in precipitation minus evaporation will be negative across the subtropics. Now remember, on a previous slide we showed that P minus E is already negative when zonally average across the subtropics, meaning that those are already parts of the world where in general there's more evaporation than there is precipitation. Obviously, particularly over subtropical oceans, they're a major source region for water vapor for the whole world. But in our warmer world, the models are telling us that that's even going to be more so. We're going to have even more evaporation happening in the subtropics. That's not so hard to picture why that would be. Presumably the oceans themselves are warmer. It's easier to evaporate the warmer water. And the air near the surface is warmer, and warmer air can hold more water vapor. So overall, there's a net increase in the total amount of evaporation coming off of the subtropics, and that is being used to increase precipitation both in the tropics and certainly up near the poles as well. I mean, you can see that in all the model simulations, both in the Arctic and in the Antarctic, we clearly have precipitation increases across that part of the world. Not so hard to really understand why. This is where the greatest amount of increase in temperature is happening. So whereas air masses that come into the Arctic now have effectively no water vapor in them, I mean they're so cold, now they're going to be considerably warmer, they can carry a statistically significant amount of water vapor into the Arctic or into the Antarctic, and therefore there can be a dramatic increase in the amount of precipitation falling in the Arctic or in the Antarctic. Very complicated stuff from the point of view of glaciology and the studies of the cryosphere and so on. Now in the case of both the Arctic and the Antarctic, that increased precipitation is in fact almost exactly balanced in the models by increased evaporation off of the Arctic and the Antarctic as well. I mean, just thinking in terms of the Arctic, as we have a warmer Arctic, we break open the sea ice, there's cracks in the sea ice and so on, leads is the right word for that. It's now easier for the ocean to be exposed to the atmosphere in the Arctic, and therefore you can have more evaporation off of the ocean into the atmosphere of the Arctic as well. Both of which are bad signs about future climate. I mean, this is not what the natural environment that we're used to living in is. Let's take another look here at the mean water cycle that we're going to be seeing in the future here. And again, we're just examining one particular panel of a figure, I can't read it off here, 1116 or 7, maybe 1114, I can't quite tell, from the IPCC report. And as we zoom in on this here, what we're seeing here is how evaporation is changing. Now remember, these panels here are an ensemble of 42 model runs. I can't read on this particular site. Yeah, I can actually. It's RCP 4.5. So a particular set of boundary conditions are running here, and then we are running the models 42 different models, so it's an ensemble. And so we can see that across the, let's see, blue means more evaporation and red means less evaporation in those parts of the world. And you can see that most places are showing more evaporation, which is clearly just a Clausius-Clapeyron equation thing, right? It's warmer, the air can hold more water vapor, and so on. Although there are certainly plenty of places where there is so much variation between one model and the next, between the different members of the ensemble, that for a lot of the world we actually don't have very good statistical significance of this result. What they're showing here is actually slightly different than statistical significance, but it's kind of a measure of their certainty that they have this right. And remember, the cross-hatched areas are the areas where they're concerned that there may be problems because there's so much variation between the 42 different members of the ensemble. But there's no doubt about it. I mean, if we switch over here to this panel here about change in specific humidity, where remember, specific humidity is sort of an absolute measure of how much water vapor there is in the air. Well, the blue colors are increases in specific humidity between the present and the middle of the 21st century, and, well, literally everywhere in the world is showing an increase in specific humidity. So, everywhere while water vapor is increasing in the world, remember water vapor is a greenhouse gas, it produces a greenhouse water vapor feedback on climate and so on. And you can see by the stippling on that diagram there, that is where basically all 42 of the models are in agreement about the sign of this change. And you can see that it's basically the entire world. Okay, this we are quite confident about, that their world is becoming more humid in the sense of the absolute amount of water vapor in the atmosphere as a consequence of the global warming. Now that is different though than relative humidity. Remember from like ATSEVS533, you learned that relative humidity is about both temperature and the amount of water vapor that's in the atmosphere. It's a measure of how close the air is to being saturated. So when air becomes warmer, if you don't increase the amount of water vapor that's in the air, you actually get the air farther from being saturated. It's a little bit complicated of an idea to sort out, and if you're not remembering relative humidity well from, intro or something like that, just use one of your mechanisms here to get a hold of me. That's probably better than me reinventing the wheel of relative humidity. But what I want you to notice is that there's sort of a pattern to areas where it's brown, where they're showing a relative humidity is actually decreasing in the future, and blue, where they're showing that relative humidity is actually increasing in the future. Mostly, the places that are brown are over land, and the places that are blue are over the ocean. This actually makes a lot of sense. Over the land, the temperature change is much greater than the temperature change over the ocean. We've talked before about the fact that it's harder because of the higher specific heat of the oceans and so on. We expect there to be bigger temperature changes in general over land than over the ocean. Well, over land, then we are having a bigger temperature change. It's probably in terms of absolute amount of water vapor, it's actually increased over land too. In fact, that's what we saw on the previous slide. But because the temperature increased more over land, we actually have a lower relative humidity over land. Whereas over ocean, where the temperature changes are relatively small, but we still have an increase in the amount of water vapor in the atmosphere, we get a higher relative humidity over the ocean. So that's actually a really good result that shows that the results are consistent and so on with the physics of the atmosphere. Now there's other panels on here that show things like changes in soil moisture and changes in evaporation minus precipitation locally and so on. I'll let the IPCC 5th assessment report tell you about what you're actually supposed to make of those results. I think that's probably a better use of your time than me picking that apart for you. But what's kind of more interesting is about what this means for extreme precipitation events. Now, we've had diagrams like this before in this lecture and in other lectures where we are talking about, in these model runs, comparing the present to the middle of the 21st century, how often are the extreme events happening? Now, at this point, what we're talking about is very wet days, which is a particular statistic that the modeling community uses, where they're saying how often is there an amount of rainfall at a location that is greater than what you would see 90% of the time before the warming happened, right? So this is a measure then of how often extreme events are happening. And again, if there was no change in this here, I'm sorry, it's actually 95% of the time, but anyway, the point is, on this curve here, it is a little bit complicated. Compared to the very warm days and the very cold days statistic that we saw earlier, how they actually define the very wet days is a bit wonky. I won't get all bogged down into how exactly that's defined, because it has to throw out the days where there's no precipitation, and yeah, it's a complicated statistic. But the basic idea is to notice that as we move forward from the early parts of the 21st century towards the late parts of the 21st century, all of our scenarios involve very wet days increasing. Now, of course, we don't know anything about very dry days from this particular statistic, but in general, extreme precipitation events do become dramatically more common in this warmer and more humid world, okay? Now again, that might not be exactly your perception of what you thought global warming would mean, because I mean, I get it. The 100 level climate change course has a dramatic figure. I wish I had a copy of the book handy with me. The textbook has this dramatic picture of like a dead tree with ground around it that is all cracked and dry and stuff like that. And that is certainly what like popular culture is, the vision of global warming is, but in fact it's kind of the opposite. Global warming tells us that a lot of areas of the world are going to be wetter, and a lot of the areas of the world are going to see a lot more of the very wet, the very high impact events. That's the kind of thing that people who are involved in policy and planning and infrastructure and so on need to know. If your storm sewer system is designed to handle all but the 1% greatest rainfall events, but the 1% greatest rainfall, whatever that threshold is, let's just say 2 inches an hour, if that's going to go from being something that happens 1% of the time when it rains to happening 40% of the time when it rains, you need to know that as a planner and so on. Cool. All right. In our next lecture, we're going to go forward even farther and start thinking more about what the models are telling us about different aspects of the Earth, atmosphere, ocean system, and how that's going to be impacted by warming, at least according to the models, in the context of modeling and so on. But before we go, let's answer a couple quick more questions here. Question 9. Climate models tell us to expect that the total amount of water vapor in the air, that is the specific humidity, near the surface of the Earth will generally blank between now and the middle of the 21st century. Will it increase, decrease, or trick question models don't make predictions about the humidity of the atmosphere in future climates? Make a choice. Make a thoughtful choice from those 3 options, and let's get a little feedback before we move on to question 10.